topic of today's video will be harmonic function, right? And as we have been discussing in our last video, the analytic function, and in this video we will be discussing about the behavior of an analytic function, especially of its real and imaginary part, that is small u and small v, right? First I will define what is a harmonic function, right? To define a harmonic function, we need a function of two variables. Suppose phi is a function of two variables x and y, right? A function phi x comma y, function of two variables, right? Having continuous first and second order partial derivatives, right, which satisfy the Laplace equation, that is del square phi over del x square plus del 2 phi over del y2 equal to 0, is called a harmonic function, right? So you need a function of two variables x and y, right, with its continuous first and second order partial derivatives, that is del phi over del x, del phi over del y should be continuous, and del square phi over del x square and del square phi over del y square should be continuous. And if they satisfy this Laplace equation, it's called Laplace equation, right? And then we say that the function is harmonic function, right? And let me take an example of it. For example, phi x comma y equal to xy is harmonic. And one more thing, since we are calling it as a function, it should be defined over some domain D. So function partial derivatives is called harmonic function on domain D, right? On domain D, right? Satisfy, right? So since it is a function, you need some domain D, and by saying that it is a domain D, it should be an open set, right? Okay, I will show that this function is harmonic on the whole complex plane. Its domain is the whole complex plane, and you can easily see that if I find del phi over del x, that will be equal to y, and del phi over del y should be equal to x, right? Then finding its double derivative, and del square phi over del x square is equal to 0, and del square phi over del y square equal to 0, right? And then del square phi over del x square plus del square phi over del y square equal to 0, right? That's why it is a harmonic function, right? Now, since we are discussing an analytic function, and we are interested in the properties of an analytic function, and one of the beautiful properties of an analytic function, especially for its real and imaginary part, that is small u and small v, is that they satisfy this Laplace equation, right? Means if fz is equal to u plus iota v is an analytic function on a domain D, then its a real part, that is small u, and its imaginary part, that is small v, satisfy this Laplace equation on that domain D, right? So I am writing that statement, or we should say that is the theorem. The statement of the theorem is, if fz equal to u plus iota v is analytic on domain D, then u and v are harmonic functions, on domain D, right? There is the individually satisfy this Laplace equation, both u and v, right? We have a small proof for it. Proof. Let fz equal to u plus iota v is analytic on domain D, right? And if we say that this fz is analytic on domain D, then they must satisfy the CR equations, which are then del u over del x is equal to del v over del y, and del u over del y is equal to negative of del v over del x, right? Okay, so taking this first CR equation, we will differentiate it with respect to x, right, and this with respect to y, right? Or should I number it 1 and 2? 1 and this is 2, right? So differentiating first with respect to x, partially with respect to x, differentiating first partially with respect to x, you will get del square u over del x square, and we can write it as uxx. It indicates that del square u over del x square, double derivative, is equal to vxy, right? And similarly, differentiating second partially with respect to y, this equation with respect to y, you will get uyy, a double derivative of u with respect to y, is equal to negative of vyx, right? And let me call it equation number 3 and 4, 3 and 4, right? Okay, since all the derivatives are continuous, since ux, uy, vx and vy are continuous on D, and this is the one of the criteria of the analyticity, right? First is the CR equations, and the second one is the continuity of these partial derivatives and functions u and v also, right? And since they are continuous on D, therefore u v xy should be equal to vyx. You should note this step. And the mixed partial derivative of v, del square v over del x del y, is actually equal to del square v over del y del x under certain conditions, right? And that condition is the continuity of these partial derivatives, right? However, this is not true in general, but if the first order derivatives are continuous on domain D, then the mixed derivative is also equal, right? Okay, then using third and fourth, right? From third and fourth, right? Ux should be equal to negative of uyy, using this, right? If you assume that these mixed derivatives are equal, then uxx will be equal to negative of uyy, right? And that will give me, implies uxx plus uyy equal to 0, which implies that u is a harmonic, implies that uxy is harmonic function on domain D, right? And similarly, we can prove the result for V also, right? By differentiating equation number 1 with respect to y, and then this second with respect to x, and then on comparing like I did in this case, right? So ultimately, we get the result that if a function fz is the analytic function u plus iota v, then its real and imaginary part, they both satisfy this Laplace equation, or we can say that u and v are harmonic functions on domain D, right? And one more thing, this v is called, note this step, note, if uxy is harmonic function on domain D, right, and there exists a function vxy which is also harmonic on D such that Fz is equal to U plus eta V is analytic, then we say that V is called harmonic conjugate of U, right? So we have one harmonic function, use a harmonic function on D, domain D, and there exists another harmonic function which is V on the same domain D, right? Such that if you add them this way, U plus eta times of V, and that function is an analytic function, then we say that this V is a harmonic conjugate of U, right? And there are examples in which we are given this U as a harmonic function, right? And assuming that Fz equal to U plus eta V is an analytic function on the same domain D, we have to search for its harmonic conjugate V, right? Means the problem is to find the harmonic function V when the other harmonic function is given, U is given, right? Assuming that the function U plus eta V is an analytic function. Okay, right. And one more thing, that we say that V is harmonic conjugate of U, that is absolutely true, but we cannot say that U is harmonic conjugate of V. However, in some textbook it is written that U and V are called both harmonic conjugates of each other. That is not absolutely true. The only thing is that if V is harmonic conjugate of U, right, then we can say that minus U is harmonic conjugate of V. I will prove that in one of our examples, right? First I will take the simplest example. Okay, fine. Example number 1. Show that U x comma y equal to x square minus y square is harmonic function on the whole complex plane D, entire complex plane C, right? We have to show that this is a harmonic function. This is the first part of the problem, showing it harmonic. That is very easy, right? We'll follow this procedure. And I will add one more thing to find its harmonic conjugate, that is V. Also find its harmonic conjugate V x comma y such that Fz equal to U plus eta V is analytic function, right? Also find Fz. Also find Fz, right? So we have a problem consisting of 3 parts, right? The first part, you have to show that this is harmonic. That is very easy. Solution. Since here U as a function of x and y is x square minus y square, you can see that, right? And if you find the double derivative of U with respect to x, I'm not finding that. Uxx means del square U over del x square will be 2, right? And del square U over del y square will be minus 2. You can find them, and then you see that, observe that Uxx plus Uyy equal to 2 plus minus 2, and that is ultimately 0, right? And this is the value of the second pure derivative with respect to x. This is the derivative, second derivative with respect to y, and you can see that they are added to give 0, right? Implies that, which implies that U is harmonic. Okay. Now second part is that also find its harmonic conjugate V. So there are certain methods to find conjugate V. I will show you 2 of those methods, right? The first one is if I see, since, yeah, or should I write it as harmonic conjugate? Harmonic conjugate Vxy. I'm going to find harmonic conjugate, right? And you see that if you find a del u over del x, del u over del x, that will be equal to 2x, and if you find del u over del y, that will be minus of 2y, right? Okay. Since I need v, and then I will use Cauchy-Riemann equation. Since the function is analytic, it is given that the function is analytic, right? We have to assume that the function is analytic. So if the function is analytic, then it will satisfy the CR equations, right? And by using CR equations, del u by del x is actually equal to del v over del y, right? And this del u over del y is actually equal to negative of del v over del x, right? Using CR equations, we get del v over del y equal to 2x, and this will be del v over del x, negative of this equal to negative of 2y. You can see that, right? Fine. Okay, then this will give you, or del v over del x equal to 2y. Fine. Now I will take this equation and will integrate on both sides with respect to y. Since I have this del v over del y here, this del y will go here and will integrate with respect to y, right? On integration with respect to y, right, this equation, first one, right, I will get v, and remember that v is a function of x and y. Both u and v are a function of x and y, so you should write v as a function of x and y in a precise way. And integration of this with respect to y will be 2xy, right? And since when we integrate, then we write the constant of integration, that's called arbitrary constant. But notice one thing, this v is a function of two variables, right? And you have integrated it with respect to y, right? Then writing a constant means a function of x, because you are integrating with respect to y, then everything that is in terms of x will be a constant, right? The constant of integration is replaced here by a new function fx, f of x, and this fx is the constant of integration, because this will be treated as a constant because we are integrating with respect to y, not with respect to x. So any function of x will be treated as a constant. That's why you should write fx here, not c, right? Okay. Now this is my fxy, well, vxy. I need vxy, so I have found vxy, but what about this fx, right? To find this fx, I need this equation, the second equation, this one also. Let me call it equation number, this is 1 and this is 2, and on integration first on integration with respect to y gives this, and I need to use this equation number 2 also. Then I will differentiate it rather, right, with respect to x, because I need del v by del x, I need to use this equation del v by del x, so you should differentiate this with respect to x. However, this result has been obtained by integrating with respect to y, right? Now you will differentiate it with respect to x, right? Differentiate partially with respect to x, this result, right? Now differentiating with respect to x will give del v over del x equal to 2y plus f dash x. You can see that this is a pure function of x, so derivative of this fx with respect to x will be f dash x simply, right? And now you can compare these two equations. Let me call it equation number 3. On comparing second and third, you can see that this 2y is 2y, but this f dash x should be equal to 0, right? On comparing second and third, you get f dash x equal to 0, right? And now I will integrate this. On integration of f dash x, I will get fx, and integration of 0 will be c. Implies that fx equal to c. C is the constant of integration. Now you can write the constant of integration, because this is not a function of two variables, right? Whenever we have a function of two variables and we apply integration, we don't write c, we write some arbitrary function, right? Constant. Okay. Now you put this constant fx is equal to c here. Where is my v? This is my v. This was my v. I will put my fx here. That will be my answer, right? Okay. I will rub it first. putting this fx is equal to c here in my v, therefore vxy equal to 2xy plus value of fx, that is c, is the harmonic conjugate, is the harmonic conjugate of u xy equal to x square minus y square, right? So this is our second part. Now the third part, find fz, right? And that is very easy. Then fz should be equal to u plus iota v, and what is u? U is x square minus y square plus iota times 2xy plus c. So you can write it as x square minus y square plus iota times 2xy plus iota c, right? And this is actually equal to x plus iota y whole square, and this is iota c can be written as another constant, or you should write it as iota c, no problem. That will be z square plus iota c. This is fz, right? In terms of z, this is an analytic function, right? Okay, now I will take another example, example number 2, and that is a very easy part, showing the u is harmonic, right? We will not repeat it again, rather we should start from here. I will have some u, and that is if u x comma y equal to x cube minus 5xy square, and if I take minus 5y, I think this should be changed, it should be 3, right? Okay, is harmonic. I'm assuming that it's harmonic. You can see that derivating it with respect to x twice and with respect to y, and then you will add them, it will satisfy the Laplace equation, right? This is harmonic function, right? On entire complex plane, right? Then find its harmonic conjugate v x comma y. Solution: you find del u over del x, that is equal to 3x square minus 3y square, right? Del u over del x will be this, and del u over del y will be minus 6xy minus 5, right? Okay, then using CR equations, I will get del v over del y equal to 3x square minus 3y square. This is equation number 1, and this will be negative of del v over del x is equal to negative common 6xy plus 5, and this negative will be cancelled finally. Okay, this is equation number 2, right? Now similar to this, I will integrate it first with respect to y, obviously. On integration of equation number 1 with respect to y will give me, integration of this will be v, and since v is a function of x and y, and that will be 3x square y minus y cube, and since we need arbitrary constant, and that will be an arbitrary function of x, right, plus fx. Fine, so this is my vxy, but it has an arbitrary function fx, right? Okay, then I will differentiate it with respect to x in order to compare with this equation number 2. Differentiate partially with respect to x, we will get del v over del x equal to 6xy plus f dash x, right? And now you can compare equation second and third, right? You can see that, and this minus and minus are cancelled. Now I will remove this minus. Okay, fine. Then f dash x should be equal to 5, right? on comparing second and third, we'll get f dash x equal to 5, right? And on integrating it, on integration, it will give me fx is equal to 5x plus c on integration. C is a constant of integration, right? Then I will put this fx here in my v. Therefore, vxy is equal to 3x square y minus y cube plus 5x plus c, right, is harmonic conjugate of u, given u, that is given in question, right? Okay, and as I said earlier that we have one more method to find this v, and I will show that method as an alternate method. Alternate method to find harmonic conjugate v, right? And that method is using the formula for total derivative, right? If you remember the formula of total derivative from the first semester course, if you say that v is a function of x and y, we know that u and v both are functions of x and y. Since v is a function of x and y, then we have a formula to find dv, right? And that is del v over del x multiplied by dx plus del v over del y multiplied by dy, right? I am going to use that formula using the total derivative formula. Dv is equal to del v over del x dx plus del v over del y into dy. Since we need v, right, u is given in the question. If v is given in question, then we will write this formula for u, and similarly, right? And then using CR equations, you have to use CR equations, right? This will become dv equal to, since del v over del x is actually equal to minus of del u over del y, right? Negative of del u over del y dx plus del v over del x is equal to del u over del x dy. Okay, now I have this del u over del y is present here. Is that del u over del y? This is my del u over del y, and this is del u over del x, right? Okay, it implies that dv equal to the negative of del u over del y, that is actually equal to 6xy plus 5 dx del u over del x, that is 3x square minus 3y square dy, right? Now the only thing which is remaining is to integrate it, but remember that this is something different, that it is involving dx also and dy also, means we have to integrate with respect to x also and y also. And if you remember that it is an exact differential equation of the form m dx plus n dy, right? And you can see that del m over del y is equal to del n over del x, right? Since I will call it equation number 1. Equation number 1 is exact differential equation, right? Differential equation. As you can see that del over del y of this thing, 6xy plus 5, is actually equal to del over del x of 3x square minus 3y square, right? This is a condition for exactness of a differential equation of this form, m dx plus n dy is equal to, right? Then the solution of this exact differential equation is given by this is a method that is given by v is equal to I have integrated it with respect to v is equal to integration of this, integration 6xy plus 5 dx, and while integrating this with respect to x, we treat y as a constant, treat y as constant, right? Plus integration of this thing 3x square minus 3y square dy, and when we integrate with respect to y, we treat x as constant, obviously, treat x as constant. And one more thing, and ignoring the terms already occurred in integration of 6xy plus 5 dx. So this is an important part. When you integrate this with respect to y, obviously we'll treat x as constant, right? But you will ignore those terms which already appeared in the integration of this first term, right? Okay. Then you will get v is equal to integration of this with respect to x will be 6x square by 2. I think that will be 3x square y, and integration of this will be 5x. You can see that we have two terms, right, from the first integral, and integration of this with respect to y will give 3x square y, right, 3x square y. But you can see that this term has already occurred here, so I will not write this term, right, following this rule, and integration of this will give me minus y cube, right, and obviously plus c, constant of integration, right. So this is my v, okay, v xy. Should I write it as v as a function of x and y? And you can see that this result is indeed the same as we achieved from this method. You can compare 3x square y minus y cube, yeah, plus 5x plus c. The result is same, right? So this is an alternate method to find the harmonic conjugate of u, that's v, right? Both methods are easy. And now I will try to write the definition of harmonic function when it is given in polar form, right? So Laplace equation in polar form. In polar form, right? Del square phi over del r square plus 1 over r del phi over del r plus 1 over r square del square phi over del theta square equal to 0 is the Laplace equation in polar form. Laplace equation, right, in polar form. And obviously, if a function is given in terms of polar coordinate, right, as we did in our last video, then you will check the condition of harmonic function by this equation, right? Okay, so I will take one example. Example number 1. If u is equal to log r, right? U is a function of r and theta. I should write it u as a function of r and theta, right? Show that u is equal to this is a harmonic function on c minus 0, right? Also find its harmonic conjugate. Also find its harmonic conjugate v r theta, right? Fine. Okay. So you are given u, and first you have to show that it is a harmonic function since u is given in terms of r and theta, right? So I will be going to use this equation, right? Laplace equation in polar form. Fine. Solution. You just find these derivatives, second order derivative, first order derivative, just okay. U is equal to this much. You first find del u, since del u over del r, that will be I think 1 over r, right? And then you find del square u over del r square, that will be minus 1 over r square, and then you find del u over del theta, I think that will be 0, right? And then you find del square u over del theta square, that is again 0, right? So you need just 3 derivatives. First is this one, then second is this, and third in this. Plug these derivatives here in this Laplace equation. Since now del square u over del r square plus 1 over r del u over del r plus 1 over r square del square u over del r square equal to theta square. Sorry, the value of this is minus 1 by r square plus 1 by r multiplied by del u by del r, and that is 1 by r, and this is 0, and I'm getting 0, right? You can see that these terms are cancelled in calculation, right? So we can say that therefore u r comma theta equal to log r is harmonic function on the domain is also important. Since we are writing its function, domain is important, and you can see that these derivatives, this is 1 upon r, this is not defined at r equal to 0, right? This is not defined at r equal to 0, even this u is not defined at r equal to 0. So we have to exclude the 0 from the whole complex plane, right? And that's why the domain should be this c minus 0, right? Origin is excluded on c minus 0, right? Okay. Now the second part, to find its harmonic conjugate Vr theta, right? To find harmonic conjugate Vr comma theta, there are two methods. I may use this method also, right? So writing dv equal to del v over del r dr plus del v over r del theta d theta, right? Okay. Since we are dealing with the polar form, so dx is replaced by del r and dy is replaced by r del theta, right? Okay. So using CR equations, that will be dv equal to del v by del r is actually equal to, I should write CR equations here first. In CR equations, that are del u over del r is equal to 1 over r del v over del theta, and the second equation is del u over r del theta is equal to negative of del v over del r. So I will use these equations using CR equations. Okay, dv equal to del v over del r is actually equal to negative of this thing, negative of del u over r del theta dr, fine, and del v over r del theta, where is that? Yes, that is equal to del u by del r d theta, right? Then integrating it or putting its value, the value of this thing, where is that? Del u over del theta, that is 0. Okay, this will give me dv equal to, this is 0, and this del u over del r is actually 1 by r d theta, right? And okay, something is wrong. If I integrate this with respect to theta, then I will get v is equal to theta by r plus c. No, that will be wrong. V is equal to theta by r plus c. And what is r? It should be theta only. Something is missing. R is missing here, I think. Del v by del theta, del v by del r. Okay, fine. I think it should be del v by del theta only. Okay, fine. Okay, it is del v by del r and del v by del theta, fine. Okay, and now here I will have del v by del theta is equal to r into this thing, r multiplied by this thing. Okay, fine. Then the value of this is 0 and the value del u by del r is 1 by r, and that is actually equal to, okay, 1 by r into r d theta. Okay, that will give me dv equal to d theta, and on integration that will give me v as a function of r and theta is equal to theta plus c. C is a constant of integration, right? And then this is my harmonic conjugate of u log r, and we can construct the analytic function also. However, it is not asked in question. I should add it here. Also find f of z or f of r e to the power iota theta, right? Then it will be f z equal to u plus iota v, that will be log r plus iota theta, right? And if you want the function in terms of z, then you have to do some manipulation, like you can write it as log r plus log e to the power iota theta, right? In order to transform in terms of z, right? Then using the log rule, it will become log r times e to the power iota theta, and ultimately that will become log z. If you remember that z is equal to r into e to the power iota theta, right? This is a function in terms of z, right? So taking another example, last example of this harmonic conjugate. Example number 2, right? Find harmonic conjugate of ur comma theta equal to r cube cos 3 theta, right? So u is given, and since the question asks about the harmonic conjugate of this, it is clear that this is an harmonic function, right? Means this is a part of analytic function u plus iota v, right? You are given u and you need v, so that f is equal to u plus iota v is an analytic function. You are assuming that it is an analytic function. Whenever this harmonic conjugate word is used, it is obvious that it is a part of an analytic function. So you will be going to use CR equations freely, right? So first finding, del u over del r, that will be I think 3r square cos 3 theta, and then finding del u over del theta, right? Am I right? And that will be equal to how much? Minus of 3 r cube sine 3 theta, and I also need del square u over del square u over del r square, that will be 6 r cos 3 theta, and I also need del square u over del theta square, yes, and del square u over del theta square, that will be differentiating it again with respect to, that will be 9 r cube cos 3 theta, right? Now plugging these derivatives in my Laplace equation, now del square u over del r square plus 1 by r del u over del r plus del square u over del theta square equal to the value of these derivatives. You can see that 6, here we have 1 over r square, also 1 over r square, 6 r cos 3 theta plus 1 by r multiplied by del u by del r, then that is actually equal to 3 r square cos 3 theta, and then the third term, where is that? I think, okay, this is negative. One term should be negative, del square u over del r square, where is that? This is del square u over del r square, this is fine, this is also fine, and what we did, we differentiated, okay, that will be minus 9, yeah, then 1 over r square and minus 9 r cube cos 3 theta, and we are getting 0. You can see that 6 plus 3 9, and cancelled out, that will give me 0, right? Therefore u r theta is harmonic function, right? Now we will search v r theta, its harmonic conjugate, using the formula v dv equal to del v over del r dr, this formula, where is that? This one, plus del v over del theta d theta, and using CR equations again, So del v over del r will be replaced by del v over del r is replaced by this thing minus del u over r del theta and dr plus r del u over del r d theta using CR equations in polar form, right? And then putting the values of this del u over del theta, where is that? This is del u over del theta, and that will give me or dv equal to del u over del theta over r, that will be 3r square, I think 3r square sine 3 theta dr, fine. And then r times del u by del r, where is that? This is, that will be, I think 3 r cube cos 3 theta d theta, right? And again we can see that this equation is an exact differential equation, right? Then we'll just integrate it using that rule, integrate. That will give me v as a function of r and theta, and integration of this with respect to r will be r cube, treating theta as constant, right? And on integration this with respect to theta, treating r as constant and avoiding the repeating terms, right? And that will give me integration of this with respect to theta will be sine r cube sine 3 theta, right? And that has already occurred here, so I will not write that term, right? That's it, plus c. C is a constant of integration, fine. This is my v, harmonic conjugate, right? Is harmonic conjugate of u r theta, that is given in question, right? And we can again find fz also, right? Also fz equal to u plus iota v, we know that, equal to u is given, that is r cube cos 3 theta, r cube cos 3 theta plus iota r cube sine 3 theta plus iota c, and then taking r cube common from here, I will get r cube cos 3 theta plus iota sine 3 theta plus iota c, and this will become e to the power iota 3 theta, and that is e to the power iota theta whole cube, I think, okay, fine, plus iota c, and this will be z cube plus c iota c, right? So the answer is in terms of z only, right? So this is the analytic function. Okay, so I will try to prove the conjugacy of u and v. Means we say that y v is harmonic conjugate of u, then what is the harmonic conjugate of v, right? Okay. Example number 3. If u is harmonic conjugate of v, then dash dash is harmonic conjugate of v, right? So you are given that, sorry, v is harmonic conjugate of u, and what is the harmonic conjugate of u, right? What is harmonic conjugate of u, right? Solution: since v xy is harmonic conjugate of u, right? Therefore, there should be an analytic function fz equal to u plus iota v is analytic, right? Because we are saying that v is the harmonic conjugate of u, it means that both u and v are harmonic. First thing is that, and second thing is that fz equal to u plus iota v should be an analytic function, right? And if this is an analytic function, then it must satisfy the CR equations, right? Del u over del x is equal to del v over del y, and del u over del y is equal to negative of del v over del x must hold by CR equations, right? Okay, I will call them equation number 1 and 3, fine. Now we have to find the harmonic conjugate of V, right? Okay, harmonic conjugate of V means that this time V will be taken as the real part of some new function. Let the function be gz, right? Gz is a new function for which the V is the real part, and you have to search for the imaginary part such that V plus iota of that unknown function is an analytic function, right? Let Gz, right, is equal to, the real part is given, right, V plus iota, and let me call it W, right, be analytic, right? You are given that V is an harmonic function and the real part of some function, and you need W, right? Okay, fine. So you need to search this W, where W as a function of xy is required, right? Now you assume that this is an analytic function, fine. So it must satisfy CR equations. Then by CR equations, differentiating this with respect to x, it should be equal to differentiation of this with respect to y, right? Okay, and differentiation partial derivative of this with respect to y should be equal to negative of partial differentiation of w with respect to x. These results are obvious from the CR equations, right? We are assuming that this is an analytic function, and why we are assuming that? Because the question asks about the harmonic conjugate of V, right? And whenever the question asks about the harmonic conjugate of some function, that function should be taken as a real part of function, right? Okay, so I have taken V as the real part second time. First time U as a real part, and second time V as a real part. I need W, right? Okay. Then using these equations, I should call them equation number 1, both these equations, okay. Then since Vx, this will give me, Vx is actually equal to negative of Uy equal to Wy, right? And what do I need? Yeah, I will integrate them with respect to y. That will give me W equal to U, or W equal to U plus C, W equal to minus U plus C, fine. And this will give me Vy equal to how much? Ux, Ux equal to minus Wx, right? Using first, right? And now you can see that this is del U over del Y, negative of del U over del Y. This is del W over del Y, and you can integrate on both sides. And on integration of both sides with respect to Y, you will have, let me call it equation number 2. On integrating equation number 2, I will get negative of U as a function of xy, obviously, equal to W as a function of xy. Since I am integrating with respect to y, then the constant should be fx, right? Where fx is the constant of integration, right? I have integrated equation number 2, right? Equation number 3 is still untouched, right? Now I will be going to differentiate this with respect to x. Why with respect to x? Because third equation has del u over del x, right? I will differentiate it with respect to x. Differentiate, I will put a box on this because temporarily this is my u or this is my w, right? Differentiating with respect to x partially, that will give me minus ux is equal to wx plus f dash x, right? Now I will compare this equation number 4 with this equation number 3, right? On comparing third and fourth, you can compare them. Ux is equal to ux, or you should take negative here, right? Then okay, we need what? We need w, right? Wx equal to wx, okay. Then f dash x will be equal to 0. F dash x equal to 0, and on integration it will imply fx is equal to constant c, right? Then therefore substituting it here, minus u equal to w plus c, or you can say that w is equal to minus u plus c, right? Therefore you have find the harmonic conjugate w You can see from here, you can see that W is the harmonic conjugate of V. So I will say that minus U plus C is harmonic conjugate of U. Therefore, minus U plus C is harmonic conjugate of V. Right. So you can see the converse part of this, right? If F equal to U plus iota V is analytic, then we say that V is harmonic conjugate of U, but we cannot say that U is harmonic conjugate of V, right? Be very careful. We will say that minus U plus C is harmonic conjugate of V, or simply if you take C is equal to 0, because C is an arbitrary constant, you can choose it 0. You will say that minus U is harmonic conjugate of V, right? V is harmonic conjugate of U and minus U is harmonic conjugate of V, right? Okay. So this is it for the harmonic function, and we have discussed both type of Laplace equation, Cartesian form as well as polar form, right? And in the next video we'll be doing something new about the analytic function. That's it for this video. Thanks.